We're going to start chapter 18, and chapter 18 is the chemistry and the environment. You can take a whole class on environmental chemistry. We're just going to cover some of the little stuff, okay? Um, One of the most important things if you study environmental chemistry is the atmosphere, the air that we breathe and everything else. There's different layers to the atmosphere, as you can see over here. We're down in here. This is where most of our atmosphere is in the troposphere. This is where we live. And basically why there's so much atmosphere down here? Gravity. But you can see as you go up stratosphere, if you fly in a plane, that's where you fly. There's a mesosphere, and the thermosphere is way up. And the nice thing about these changes is it goes really cold and really hot. So if a meteorite starts here, because of the changes in temperature, it basically shatters by the time it gets to us. So we don't have, like the movies where we have this huge, enormous rock, destroying the earth. And you also see in between, they have what they call pauses. Those are like in between the stratosphere and the troposphere, we have the tropopause, and there's stratopause and the mesopause. So anyway, the atmosphere consists of the troposphere where we live, the stratosphere. Those two combined are 99.9% of the atmosphere as far as its mass. And then you have lighter areas, the mesosphere and the thermosphere, okay? Temperatures vary greatly, like I was talking about with altitude. When you're in the troposphere where we live, as altitude increases, temperature decreases. It gets colder as you get higher. And pressure decreases, again, because it's simply just because of gravity, okay? If you live in Denver, the Mile High City, you have less oxygen in the air, lower. And when you're talking about altitudes, the lower the altitude, the more actually oxygen you have, the more atmosphere you have, okay? So when you're talking about the atmosphere, what is it made out of? Well, mostly the atmosphere is made out of gases, and it's not uniform, okay? Again, the heavier gases sink because of gravity. So the lighter ones are on top and the heavier ones on the bottom, okay? No trick there, okay? Near sea level, the majority of the atmosphere is nitrogen and oxygen. It's like 79% nitrogen and 21% oxygen, like 20.9. I mean, when you put the two of them together, there's only like 1% left that could be something else, okay? And here you can see the components, like I was saying, 78% nitrogen, 20.9, so 21%. So you only got 1% left for all the rest of this stuff. Argon, carbon dioxide, neon, helium, notice noble gases, methane, krypton, hydrogen. And one thing they left out here is water vapor. But again, these are all gases that you find in the atmosphere, okay? If you've ever seen this, and some of you have, the Northern Lights, okay? Basically, the Northern Lights is like a big flame test. You get nitrogen gases caught in between these belts, and they're like burnt, and so they give off their color. It's really, nitrogen is very unreactive because it's a triple bond. N2 has a triple bond between it. So there's a lot of energy to break that bond. Okay, here you have high energy solar particles. What they'll do is they'll create, they'll break the bonds between nitrogen, which is a triple, and then O2 is a double. Okay, and then they form these colors, and if you burn nitrogen, you get these colors. So basically, it's kind of like a huge flame test where you're moving the nitrogen from one energy level to the next. You're doing the same thing with the oxygen, okay? Oxygen has a lower bond enthalpy. In other words, they're not as disorganized or whatever. And again, they're more reactive because it's a double bond as opposed to a triple bond, okay? So that's why mostly the green colors, that's the nitrogen gas. You'll get some other purples and stuff. Those are from the oxygen, okay? If you take oxides of nonmetals, and so in other words, carbon monoxide and all that, they're very, very acidic, okay? We talked about acids and bases already. And oxides of active metals are basics. So they're bases or alkali, they called, okay? But again, if you've seen the Northern Lights, basically what you're looking at is we're moving the electrons up to another energy level. When they go back down, they release energy. It's like a big flame test, okay? So when you have this atmosphere, okay, beyond the stratosphere, way up, those are our outer defenses, okay? In part of the stratosphere, we have something called the ozone, and we'll talk about that in a minute. But we have outer defenses, and they protect us against radiation and high energy particles, okay? So up there, chemical changes that occur, they call them photodisassociation or photoionization. In other words, photo meaning light causes things to break down, to dissociate or form ions, okay? And here you can see this is kind of a spectrum of where it happens. And really the photo comes from sunlight, all right? Here's at sea level and here's way up here, the energy, all right? So again, photodisassociation, we'll talk about that in a minute, or probably next time when we talk about fog. But anytime you see photo and dissociation or photoionization, it's energy from the sun, basically, causing compounds to break down into smaller parts, into ions, okay? So you rupture, when you have photodisassociation, you rupture the bond due to the absorption of a photon. And again, that comes from the light, okay? So you're going to take a bond and you're going to break it. The ions that aren't formed, if the ions aren't formed, then you have radicals. You have unpaired electrons and they need somebody, because remember, they want that 8, they want that octet. So sometimes because you have these unpaired electrons, they'll form what they call radicals, okay? One of the most important reactions in the upper atmosphere is what they call the photodisassociation of oxygen. What happens is the oxygen, O2, breaks down, and so you have this O2 and you have this free radical oxygen, just a single oxygen, and it doesn't like to be that way. So it'll attach to it and you'll get O3, and O3 is called ozone, and you guys have probably heard of ozone before, okay? So way up, you know, this is at near the tops of the stratospheres, you have this photodisassociation of oxygen happening, okay? And here it is. You take oxygen, O2, and you add this high energy, okay? And then you end up with these, they break down into single ones, and so then what will happen is another one of these guys will grab it, and then you get O3. So one oxygen, when it breaks down, will form 2 O3s, ozone, okay? So sometimes when the molecules in the upper atmosphere absorb solar radiation, then they emit electrons. So you can have both things happen. One of them where they absorb it, one of them where they give it off, okay? Photodisassociation would be giving it off. Photoionization would be where they absorb it, okay? And when that happens, you're going to form a cation. If you remember that, that's a positive ion, okay? So here we have N2, O2, oxygen, whatever. And you notice that they're all nitrogen or oxygen, either pure nitrogen or a combination of nitrogen, okay? And the reason why is that's mostly what the atmosphere is, nitrogen and oxygen. Okay, nitrogen's number 1, oxygen's number 2. I know a lot of people think oxygen's the number 1 thing in the atmosphere, and it's not. Nitrogen is by far, but it's in a form that's very, very stable. Okay, we like to put nitrogen in our gardens. Nitrogen's great and makes our gardens grow well, but in the air as N2, it's so stable, we can't use it there. But if you've ever noticed after a lightning storm, your grass probably grew a little bit. What happens is when we get that lightning, we get that energy, it actually breaks down the N2 bonds, and then you get free nitrogen, and then your plants and your garden and your grass and everything will absorb it. So after a really good lightning storm, thunderstorm, your grass and everything else will grow better because it'll fix that free nitrogen. Okay, so back to ozone. Okay, ozone absorbs a lot of radiation, okay? Between 240 and 310 nanometers. I don't know if that makes anything to you, but it's not a big deal. The thing to remember is ozone absorbs UV radiation, okay? From the sun, we have UV radiation. We do not want it to get down to us because it'll cause us harm, okay? When I was a kid, we didn't have sunscreen because we didn't worry about this stuff. But now we do, because we have a lot more of this UV radiation coming down. And when you have that happening, when you get that dissociation, okay, here you can see the wavelengths it absorbed. Ozone is a protective layer for us. It's like a filter. It takes out the UV radiation so it doesn't get down to Earth, because UV radiation can cause, in people, skin cancer. In plants, mutations, tumors, on other animals that have to live out in the sun all the time, they don't have sunscreen, so you can have all these issues because of it. Okay, so the ozone layer is in the stratosphere, an altitude of about 25 kilometers, so you can see where most of it is happening. Okay, this is where most of our ozone is. All right, again, that's a layer that covers the Earth. It's really thin, but its job is to absorb ultraviolet radiation so it doesn't get down to Earth and cause us problems, okay? Well, we've done some things to change the Earth's atmosphere, okay? There's some natural things that occur to mess with the ozone, and then there's a lot of things that we've done to mess with it. The natural events would be like volcano eruptions. You get a lot of soot and stuff in there, and it messes with the ozone. Release of carbon dioxide from oceans, the natural occurring, that will vary the ozone layer. Lightning, like I was talking about with nitrogen, it also affects the ozone. But anytime you see the word anthropogenic, that means caused by people, okay, caused by humans, all right? So we have destroyed a lot of our ozone by what they call CFCs, and I'll show you more about that. That's chlorofluorohydrocarbons. What they do is they tie up the free oxygen, so instead of getting O3, we don't get it anymore because the chlorine and the fluorine, they steal them, okay? And another thing we've done is because we burn so many fossil fuels, oil and coal, we put a lot of extra carbon dioxide in the air, a lot of extra sulfates in the air, and then NOx, because it's NOx, because it can be NO2, it can be NO3, it can be NO4. That comes a lot from our cars. Okay, so here's the ozone layer. Okay, 1974, they discovered that chlorofluorocarbons, okay, it's a thing that we use in refrigerants and stuff like that. It could be depleting the supply of ozone in our upper atmosphere. Okay, then later on they discovered, yeah, it is. They measure ozone in what they call Dobson units. I think it's the guy that came up with a way of measuring it. But what happens is, here you can see there's a hole in the ozone. This is over Antarctica, which a lot of people didn't worry about because, you know, there's just not a whole lot of people hanging out in Antarctica. But the band got bigger and bigger. What was really cool is they actually got together, all the countries in the world, and said, you know what? We need to take care of this. This ozone problem isn't just one country's problem, it's everybody's problem. So they banned CFCs in over 100 countries, and actually the ozone depletion has been coming back. Okay, the CFCs, what they do, mostly they're using in like aerosol cans and refrigerants, and they're not water soluble. Okay, so they don't get washed out by the atmosphere when it rains and stuff. That's where we get rid of a lot of pollutants when it rains, but they don't because they're not water soluble, and they're really unreactive, so they go up higher into the stratosphere. And what will happen is it's easy to break a chlorofluorocarbon bond down. It's much easier than to break like an N2 and O3 or whatever. So it'll go up to where the ozone layer is, and this is what will happen. You know, you take chlorine and your ozone, and what it does is it basically takes off an oxygen. So you get this and oxygen, which oxygen's fine, we need oxygen, but this takes the place of our ozone layer, and we need our ozone, so our ozone layer was getting thinner and thinner all the time. Okay, so because it was destroying it, because we were converting it to oxygen and breaking down all our ozone, we got more chlorine atom concentration, but you know, it wasn't good because now we didn't have that ozone layer. Again, like I said, when I was a kid, I know that was when we rode dinosaurs and stuff, but we didn't have sunscreen. We just played outside. We didn't worry about it. But now, you know, it's huge. So what happens if you look here, you take chlorine plus 2 ozone molecules, okay? You end up with a chlorate ion. Actually, this is a hypochlorate ion, and oxygen. Well, not good. You know, what happened to the ozone? Okay, and then if you take this chlorate and then you add more energy to it, it breaks it down more into more oxygen, and instead of O3, back to O2, okay? So we're ending up destroying our ozone layer. We're creating oxygen, which isn't a bad thing, but we've got enough oxygen. We don't need oxygen in the stratosphere. We need oxygen down here. This happens up in the stratosphere. So we've got to get rid of the CFCs to make sure that the chlorine isn't up there anymore. Because they say one chlorine can take away like 1,000 or even more ozone ions. So we got to stop, you know, and we have. Actually, you're going to watch a video about that. So that's the first part of the notes. We're just going to talk about ozone in the atmosphere and what it's done to the atmosphere.